9.1, significance tests the basics. Last unit in chapter 8, we were working on confidence intervals, one of the most common statistical inference methods. And that was nice because it gave us a window of values that were reasonable values for when we went out there and did a sample, and what window might be reasonable to think that it was a. But chapter 9, what we're starting right now, it's significance tests. And significance tests are a formal procedure where we're comparing an observed data value to a claim, and we want to decide if we think it's so unusual by chance variation that this claim, maybe we don't believe the initial claim. So basically what we're doing is we're taking that mean and we're comparing it for the sample, we're comparing it to the mean for the population, or our p hat, and we're comparing that directly to the parameter, the proportion for the population. And we can do this same procedure for other, whoops, wrong symbol over there, excuse me. We can compare that with other things as well, like as long as we're comparing that sample statistic to a population parameter. So which one you decide to use is going to depend on your goal. If you're if you only have raw data, only have sample data, and you don't have a population value to compare to, then your goal is probably to estimate that population parameter. And so this is nice because it gives us a window of what we think might be reasonable values. And I mean, we either did capture it or we didn't. Significance tests, though, if we want to compare our data and somebody's made a claim about the population, then we would prefer that test to look at the outcome. So the basic idea for a test, the basic idea is that you are looking for a probability value, a p-value, and you're looking for when this p-value is very low and not likely to be the result of chance variation. Then we're going to believe that maybe our initial assumption was not correct, and that we're going to think that maybe that claim was not true in fact. Now, when we do a test, we hope we are making a correct decision, but there are actually two types of error that can occur when you're making a decision. So, thinking this through, if we have a population of human beings and they have a mean IQ of 100 on the IQ scale, we know that this population of humans, they're going to be very intelligent humans, and they're going to be humans with lower IQs as well. We know that these are all humans, and even though meeting this 68, 95, 99.7 empirical rule, we know that they're going to be 2.5% up here, and they'll be about 2.5% down here. Now, if somebody comes and we test their score, and here's my human right here with their very high IQ, I might reject that person's claim and think, hey, you're not a human, you're way too smart to be human, and then I would have committed what's called type 1 error, because I said, well, you're not a human, you're too smart to be a human, but really they are a human, so I just made a mistake. They're really a human. But what's type 2 error? So let's say that there's a group of aliens from another planet. They finally come down here to Earth, and we don't realize that they look a lot like us, so we can't tell by looking at them. But these aliens are really smart. That's pretty much why they were able to come to the Earth. And let's say that their mean IQ is about 130. And so that's what aliens do. So if an alien is out there and comes down to Earth, if maybe I would think that this alien right here, if they're over here, I would have realized that they were an alien, because that's the point where I was rejecting at this 2.5%, and I would realize they were an alien. Realize. So it's an alien. That's good, because like I didn't make a mistake. But over here on this side, here's my green alien. Here's my green alien right here on the thing, and I would have thought they were human. So when I make a mistake, I'm mistaken for a human, that's me committing the type 2 error. So, and we'll do much more with the error in the 9.2 unit. But continuing on, so the reasoning behind significance tests: if I have a basketball player and they claim to be an 80% free throw shooter, then I might want to test this claim using something like what we used in previous units, simulation. And I want to see if just by chance variation, what would happen. I send my shooter, my basketball player, I have him go out there and I say, hey, why don't you go out and shoot some baskets? Let's have you do 50 free throws. That's a good idea, because 50 is going to be greater than 30. So I'm going to meet CLT. So that's good, because I think my empirical probability is going to approach the theoretical or classical. So that's good. So him going out there and doing that, I think this will give me a good estimate of what he shoots. He goes out and he shoots 0.64. So he said he was a 0.8, but when he went out there, he got 0.64. But what do we think of this when we compare this to a simulation of this process? So the graph here shows a simulation using Fathom of 400 sets of 50 shots. So I could have done these shots by hand. Maybe I would have used a random number generator, and maybe I'll have the numbers 1 and 2. That will be when he misses. And then I'm going to need to have 8 numbers that are going to be when he makes. So 3, 4, 5, 6, 7, 8, 9, and 0 can be when he makes it. I have to get 50 50 numbers, and I am not going to ignore repeats because I have replacement, because I'm going to let every single time we're going to see those numbers, and I'm going to count how many baskets he makes and see how many he makes. So if he goes out there and he makes if he makes 32 out of 50, then boom, I put that dot right on the graph right there. That's it. And then on the next simulation, I might get a different dot, and like I keep doing this. The Fathom software did this, assuming that a person has this probability, assuming that this is how it's breaking down. These are the dots from simulations that happen. So what's the probability of our basketball player getting a number of a 0.64 or less, being that bad of a player or less, if he really is truly a 0.8 player? That would happen 3 out of 400 simulated trials. So that is a pretty low probability of that happening strictly as a result of chance variation. So when I would say that this is strong evidence against this player's claim, because it would be highly unlikely, especially if you're comparing to an alpha level of 0.05, that would be highly unlikely to happen. And that gives me convincing evidence that the player's claim is not true. Based on this evidence, we could conclude that the player's claim is incorrect, and that's what we would do with a test situation. But in this situation, because of the result we got, what could happen? He said he was 0.8. We see 0.64. We reject the 0.8. We don't believe that. So what could be true? We are correct. He does not shoot 0.8. He is really lower. We realize that. And maybe we don't invite him to play on our team. Maybe. I don't want to call him a liar, but so we might not ask him to be on our team. But then what's the other thing that could have happened? Well, we rejected him. We thought he was down here and we rejected him, but maybe he really is part of this 0.8 group of players, and so he was having a bad day. And we don't believe him. But he really does shoot at the 0.8 level. And maybe we really maybe we really want him on our team because he's a great player, but we did not believe him. He was just having a bad day, but we didn't believe him, and we just committed what's called type 1 error. That would be example of that. So that's the idea of what's going on, and we're going to be doing significance tests where we carefully look at our null hypothesis, where we give the player the benefit of that. We're going to start thinking he is P equals 0.8 player, but we're going to look for evidence against this claim, and that evidence is going to be our alternative hypothesis, or the evidence will be the p-value that we get, and then we'll be looking at the alternative hypothesis if we can reject that null. Okay, so we're going to make a claim. That will always have a symbol of equality in it. And then we will be comparing that claim to a statement of inequality. So if you look down here, and we'll find the probability of that happening. That evidence is really about the p-value, that probability of that happening. So we have, in our example, our hypothesis was that he is a 0.8 shooter because we always start out believing him, believing that he's true, and that's our null. And this can be pronounced H sub 0 or H naught or null. Some various ways to say that, but anyway, and then we're comparing it to him being below. We're looking for evidence of that. And in any significance test, the null hypothesis always has the statement of inequality in it. And so we're always going to use that statement right there. And then we are going to be looking at our alternative hypothesis. We'll be looking at if we're looking at it being less than. So if we have our parameter, maybe I'll do a mu here, and then I want to know when I get my sample, I'm interested in this probability of that happening. That would be a lower tailed case or left tail. Or maybe I'm looking for a situation of being over, and maybe this time I'm thinking of a proportion, and I get a p hat, and I'm wondering if that probability is unusual. And then there's a statement of inequality, and that would be the both sides when you're looking at, go back to mu again, and if maybe my x bar came out over here, I find this area, but the same size area is up here, and so that would be just being different. You could be higher or lower. So determining which one to use, read the problem carefully, make sure the equal sign has to be in the null. So that's the main thing there. Okay, so hypotheses will always refer to a population, not a sample. Make sure you're using population parameter symbols. It would never be correct to write a hypothesis about the sample statistic, such as the p hat or the x bar. Those would never belong in a hypothesis statement. Okay, so for each of these following problems, we're going to try to see if we can tell which one is the parameter of interest. That means parameters would be proportion, means, standard deviation for the population, and then we're going to state the appropriate hypotheses for performing the significance test. So here we have this job satisfaction assembly line workers, and they're wondering if there's a difference between being machine-paced rather than self-paced. And they're going to be looking at each individual and comparing each individual's job satisfaction for each of these types of work. See which one they prefer. So that means for the individual is going to be, the machine-paced minus the self-paced. So that means we are looking at a difference for the individuals. We're doing a matched pairs. If you read that, pairs design for this experiment. And if, so think about your symbols, mu or p, which symbol would be appropriate for this satisfaction? Well, I've already written it over there, so I guess that's a dead giveaway. But that's going to be equal to what? If they were exactly the same for myself, if I felt exactly the same for each type of pacing, then if I got a 2 on the first one, I'd get a 2 on the second one, when I subtract those, I should get 0. So if they're exactly the same, you're expecting it to be 0. And if we're testing, we have to decide, are we going to be testing it being better worse, different. Which one does it say? The response variable is the difference in satisfaction scores. They don't seem, nope, this is just telling us that we're looking at that, but they don't say anything about which symbol they are looking at, so they must just be looking to see if there's a change. This would be a change, is there any kind of difference at all? Higher, lower? So there's our two hypotheses. Okay, so think about your symbol, set up your hypotheses, set up with the numbers, make sure you're checking what direction it is describing. Okay, website, 85% of teens are getting less than 8 hours of sleep. Janie wonders whether this result works at her large high school. That's cool for independence. She asks a simple random sample of 100 students at the school how much sleep they got, and 75 of the respondents said less than 8 hours. Sometimes it's easier to think through what do you know from what's been stated in the problem, and usually this one, the p-hat, the sample statistic, is much easier to identify than the parameter. So now that I've identified the sample statistic, I can say, well, this right here is the what they're saying is nationally, that's what the population would be. So setting up H sub O, H sub A, and so I am looking at proportion. So I'm going to use P for my symbol, always an equal sign here in the null hypothesis, and that's the parameter value to go with the parameter symbol. And what do they want to know? She asks her students on a typical night, she wonders if this result is the same for her school, So she's looking for evidence of it being different, meaning not the same at her school. Okay, this part is the 2010 census marketing campaign. The U.S. Census Bureau advertises 10 questions, 10 minutes. That's all it takes. Well, we're starting the new census this year, 2020. The U.S. Census Bureau estimates that for the average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We think that the actual time it takes may be longer than advertised. Sometimes drawing a little graph to say, well, if this is the mean time it takes, we're going to be wondering if it's taking longer, something up here. So that can help me figure out when I'm writing my alternative hypothesis what symbol I'm going to be using right here. So we're thinking that the mean time they claim is 10 minutes. So I'm going to say 10 minutes right here. If you define your mu, or at least put your units someplace where, and we're wondering if my mean time is actually more than 10 minutes. So that would be a one-tailed situation that you're going to check for the census. Okay, so we're looking for evidence against this null hypothesis. And the more evidence we can find, then the lower the p-value is going to be. If things are unlikely to happen, meaning unusual to happen, that's evidence that it's not just the result, just the result of chance variability. And then I'll let you read through these pages. You can read through these pages about, what we're going to be doing. We're making a decision to reject our null or a decision to fail to reject our null. We never conclude that the null is true because we don't really know if it's true. We just know we don't have enough evidence to say it's not true. So if our sample result is too unlikely to have happened by chance, assuming that my null is true, then we'll reject it. Otherwise, we're going to fail to reject it. Never accept the null. Sometimes in some sciences, like probably in your AP Bio class, they do like to use wording that makes it sound like they're accepting the null hypothesis, but it's kind of the idea is that with the biologists is they're doing some research and they're trying to push their case for whatever thing they're researching. So they're trying to say language that makes it sound like they know what's going on. But in statistics, really, you should always leave yourself with a little way out and never sound too certain. So here's your two situations. Small p-value, you're going to reject your null. You're going to conclude that the HA is true in context. If you have a large p-value when compared to your alpha, you're going to fail to reject your null and you will not be able to conclude the HA. See how you're still making a conclusion about the alternative hypothesis, but in context. How small p-value we should require, it all depends on what significance level you've decided on. And usually we're using a 95% confidence level. So usually we're using an alpha of 0.05. Now, if it's not given in the problem, that's what we're going to go with. Sometimes they give you a different significance level or confidence level in the problem, and then you would adjust to that. Okay. So if our p-value is smaller than alpha, we're going to say that the data are statistically significant. We can use that word because we did actual calculations. Whoops. I need a smaller actual calculations. In writing, if you have no calculations, you should use the word substantial. Well, who knows how to spell that? But anyway. Okay, so when we use a fixed level of significance to draw a conclusion, here's our same from the last page. And here's some wording. My wording, you'll see that I definitely write this one more often. Maybe it's a little shorter, so that's why. And then I definitely write this one more often, but you can read the two different wordings from the book. Okay, for our job satisfaction study, we were testing these, this null and this alternative. We're testing the null actually. And then since there's no alpha level given in this problem, we'll use it at the 0.05 level. We're going to say that the null, explain what it means for the null hypothesis to be true in this setting. The null hypothesis states that there's no different in the mean of self-paced minus machine paste. So it doesn't matter which system they're using for the individual workers. So that means like you probably wouldn't want to change your whole system if they're not going to really show a difference. But if I ended up getting when I get this p-value of 0.2302, let's interpret that p-value in context. So since the p-value of 0.2302 is greater than alpha equals 0.05. Now notice I gave my number and I gave my number that I'm comparing it to. Now I'm going to make a decision. We reject. Oh, no, we fail to reject. Fail to reject the null hypothesis. So I'm just saying what my decision is. That is a close one. And there is not, because since I failed to reject, there's not significant evidence that there is a difference between machine and self-paced working. We did not find that there was a statistically significant difference. Notice how I'm using my alternative hypothesis as my conclusion here and how these things are relating to each other. So make your decision, you reject, either fail to reject, explain your decision in context, always using the alternative that you either have evidence, there is, or there is not, depending on which situation happened. So, looking at a situation with a company that has developed AAA deluxe batteries, and they're supposed to last longer than their regular AAA batteries, and we're thinking, should we change our whole production? These new batteries are more expensive to produce. Should we go out there and change all our production to like make these new batteries? We go out and we do a simple random sample of the new batteries. There are 15 new batteries, and we use them continuously until they're drained. And we want to look at, are they, if the old batteries, the population, no change, 30, if we go out there and we want to know if they're lasting more, when we get our X value, is it going to be enough evidence, our p-value, that we're going to say that we need to go and start making these more expensive batteries? If our p-value is 0.0276 at the 0.05 level, since 0.0276 is less than alpha equals 0.05, we reject the null hypothesis and there is significant evidence that the batteries last longer So what are you going to do? What are you going to do in this situation? We will make the new batteries. And so we're changing that production and making those new, more expensive batteries, but it's worth it because we saw that they seem to, based on our statistical tests, they seem to be working. But like, what if we are being a little more, we want more evidence. We don't want it just at the 0.05 level. We want more evidence before we change our whole system. So maybe this person says, I want it at the alpha equal 0.01 level. Well, in that case, since 0.0276 is greater than alpha equal 0.01, we fail. There's my difference. Reject the null hypothesis. Sentence is very, very similar, and there is not significant evidence that the batteries last longer. Notice how that's worded the same. What are we going to do about this? We've just got a result. What are you going to do with this information? We will not change our projection because we don't have these new batteries, which we failed to reject. There was not the evidence. We are going to just stay the course and keep our old batteries. Now, when you make decisions, sometimes your decisions are right and sometimes they're wrong. Sometimes you might never know what is the truth about the population. You might never know what this is, but there is a truth. There is a truth about the population, and it would be, well, whatever it is, and we may never know what it is. Now, but we're going to be going out there and getting a sample, and so based on our carefully constructed sampling routine, we get our best guess at what the population is, but based on that sample, we make a conclusion to either reject or fail to reject. We don't know if it's true, but it really has a truth. If the null is true and we've rejected the null, we have committed a type 1 error. The probability of that happening is going to be our alpha. Or if the HO was false and we rejected it, well, we made the correct conclusion. That's great. Love it when that happens. But if we fail to reject the null and the null is really true, we have made the correct conclusion. But if we fail to reject the null when the alternative was actually the truth, we have just committed type 2 error, and we use the symbol beta for that probability of that happening. So let's think about the context of what that would mean if you are making mistakes. Here we have a shipment of potatoes, a potato chip producer and its main supplier, and they agree that we want certain quality standards of these potatoes before we make them into chips. We've agreed with our supplier that if more than 8% of the potatoes in the shipment have blemishes, we don't want them. We're going to send that truck away. We want a different load of potatoes. But if we see that this is not the problem, then we're going to use that truckload and we're going to make some potato chips. So we get a sample of potatoes coming into the plant, and what would we be looking at? We'd be looking at, we don't care if those potatoes have a low number of blemishes. We only care if they have a high number of blemishes. Now, 0.08 is actually the mean that the standard would be. Our sample, whatever it comes out as, that would be the thing that we'd be testing. So we are going to be looking at a null hypothesis of 0.08 compared to the alternative. When they're bad potatoes, they're going above 0.08. But notice that the 0.08 is in the middle, and our test statistic will be the number that, well, it could show up anywhere, but if we're going to be rejecting it, it's probably going to be on the right. Now, describe the type 1 and type 2 error in this setting and the consequence of the error. So, type 1. What would happen if the truck has good potatoes with 0.08 blemishes or less, but we concluded they were over 0.08 blemished potatoes or bad potatoes, we would send away a good truckload of potatoes. And that might make our supplier really upset because they sent us good potatoes. We said, well, see you later, potatoes. We basically wasted the potatoes. They're going to be upset. We don't want to have that happen too many times because they would definitely not want to send us any more potatoes if we're just going to keep wasting them. But type 2 error, what would that be? If the truckload really is bad potatoes, is bad potatoes, and we conclude they are less than or equal to 0.08 potatoes, blemished potatoes, then what's going to happen? We're going to keep the truckload, and we will have probably make chips out of these potatoes, and we just made chips with bad potatoes. Now that is going to be a bad consequence, potatoes, with our clients. So we would probably have upset customers, and if we have that happen too many times, then, well, nobody's going to be in business because we'll be out of business, and then that truckload, the person sending us truckloads of potatoes, we won't need them because we won't be making any chips. So in this situation, this, from the manufacturer's standpoint, is definitely the worst type of error for this situation. Now, what type of error is worse is going to depend on the situation that you're studying. So that's an introduction to testing significance test basics.